Hello everyone, and welcome back to another Physics Friday, where today we are going to be deriving some of the most important results of special relativity, and then from that deriving the Klein-Gordan equation, from which we are going to find the Dirac equation. And the ultimate goal of this entire chain, starting with special relativity and going to Dirac, is to, in the next video, derive Maxwell's equations from U1 symmetry in the Dirac field. So, without further ado, let's get started with some special relativity. One of the central ideas of central relativity is the idea of the speed of light being constant between reference frames. So, what exactly does that mean? Well, if I'm standing here with my little flashlight and I shine it, I'm going to see the light that comes out of it go at the speed of light. But if I have Max Verstappen right here, who's driving his F1 car, and he turns on a flashlight that he's duct taped to the front of it, from his reference frame, he's also going to see the light go at the speed of light. But now what happens when he sees me in the stands shining my flashlight? What's the speed of light that's coming out of my flashlight? According to Galilean relativity, he's going to perceive the light that's coming out of my flashlight to be going slower than the light that's coming out of his flashlight. And from my perspective, it's going to be the opposite. But what Einstein says is that the speed of light is constant between all reference frames. So according to Einstein, in special relativity, Max would see the light coming out of my flashlight going at the exact same speed as the light that's coming out of his flashlight, going at, well, the speed of light. So where does this leave us? Well, typically in classical physics, you represent your position in space with, some sort of vector, some sort of x, and it has three components, right? It has an x component, a y component, and a z component. And, typically these are functions of time. But special relativity says that the speed of light is constant in all reference frames, which makes the timing of different events different from reference frame to reference frame, which effectively makes time another variable in this vector, making it go from 3 components to the namesake 4 component 4 vector. So what we would represent, or the way we would represent our position, quote unquote, in space-time in special relativity is going to be with a 4 vector, namely ct. The c is there to get the units to line up, because after all, we do want everything to be in, meters, so to speak, right? So we're going to have ct, x, y, and then z right here. So now that we've defined our position in this way, let's play around with what exactly our velocity might be, what our momentum might be, and what these zeroth components actually are. So say I want to find our typical velocity, right? So I want to do dx and then dt right here. And there's nothing necessarily wrong with this right here, actually. But this velocity right here is not going to be representative of what it might be in classical mechanics. Because in classical mechanics, your velocity is just, how fast you're moving, right? But in special relativity, this velocity, differentiating our position with respect to time, is going to be, the velocity, relative to some reference frame. So velocity is, always relative to something, right? So the idea of velocity then, in this sense, doesn't really make as much sense, which is why instead we introduced the idea of differentiating with respect to proper time. So instead of differentiating with respect to just normal time, we're going to differentiate with respect to proper time, which is denoted by a tau. And now a very fair question is, what on earth exactly is proper time? Well, proper time you can think of as, like the total distance, so to speak, that you're going in space-time, right? So we can think of this as, well, c squared and then dt squared. So, just writing this out in terms of differentials. The c squared, just to make sure the units line up, right, is equal to c squared dt squared minus dx squared minus dy squared minus dz squared. And now the reason for this is because our t's are just going to be temporal components, right? So in our metric that we're using, they're going to be positive, whereas our actual positions are going to be negative. So if we actually want to solve for, this relationship between dt, or our proper time, and our regular time, what we can do is just divide both sides by c squared dt squared, or divide, quote unquote, right? That way we end up getting d tau over dt squared, well, is equal to 1 minus and then, well, dx squared over dt squared minus dy squared over dt squared minus dz squared over dt squared. But that right there is just going to be the magnitude of our velocity. So right here, it's just going, or magnitude of velocity squared, sorry. So this right here is just going to be v squared, and then we also can't forget about the factor of c. So we have that c right there. So if you look back at our velocity right here, which we're going to call our proper velocity since we're differentiating with respect to proper time, well, we can apply the chain rule here, just kind of multiply, quote unquote, the top and bottom by dt, and then just swap these two, right? So instead, we end up differentiating our position with respect to time, which we know how to do, and then just deal with an extra term on the outside. So dt, d tau. So solving for this right here, we just have this right here, flip it, take the square root, and we see that dt over d tau is equal to 1 over the square root of 1 minus v squared over c squared, which is the namesake gamma right here that you always see with special relativity. And it's this factor of gamma that causes both the length contraction and time dilation. Or maybe not cause, but it's the factor by which those things are stretched, I should say. So we see that this right here is indeed just gamma, right? So gamma right here. So all we need to do is, to find our proper velocity is just find the derivative of our position with respect to time. And we're just going to do that component-wise. That still applies. So the derivative of this term right here, well, we're differentiating with respect to t. C is obviously a constant. That is, quite literally the whole point of relativity, right? So c is speed of light, constant. So that right there is just going to be c. So this right here is going to be c. And then we're going to have the derivative of x, y, and z. Just every component of our position differentiated with respect to time. So that's just going to be our velocity in the x direction, our velocity in the y direction, I should say relative velocity, and our relative velocity in the z direction, all times gamma right there. So that right there is our 4 vector for the proper velocity, which we will denote as nu right here. So now that we found our proper velocity, let's go ahead and try to figure out what exactly our momentum is going to be. Because we see here that we have our components for, our velocity is normal, but then we also have this extra c. So let's go ahead and see how that affects our momentum right here. So momentum, which will be represented as a p, is going to just be equal to, well, m times nu. It's the same thing as classical momentum, just replace relative velocity with proper velocity, right? So let's go ahead and see exactly what happens when we find the magnitude of our momentum. So one way we can do that, or denote it at least, is going to be p mu times p mu, where mu right there is just going to be the muth component of the vector, right? So for example, in our proper velocity right here, the 0th component would just be c, and the first component would be vx, and so on and so forth. So this right here is the magnitude of our momentum, which we know is just going to be m squared then, times nu mu. So multiplying these two together, we have a factor of gamma squared out front, just right here. And then we're going to just multiply the components together. So we're going to have c times c, so that's just c squared, and then vx times vx, and so on and so forth. But because this is going to be a dot product, and instead of this being a dot product in just 3D space, in which we just have a metric of ones along the diagonal. Instead, we have a metric of 1 and then 3 negative ones, right? So instead of having plus vx squared, we're actually going to have minus. So we're going to have vx squared minus vy squared, and then minus vz squared. But what exactly is this expression right here? Well, we see that this right here is just going to be, minus v squared. But what's this gamma squared term? Well, evaluating everything entirely, we have 1 minus v squared over c squared, and then just c squared minus v squared. So factoring out a factor of c squared in the numerator, we end up with this right here just being c squared. So the magnitude of our momentum right here is indeed invariant with respect to velocity, which is good because we wouldn't want that to be relative to our velocity, because it's supposed to be an invariant quantity, right? So this right here is equal to m squared times c squared. But let's think about another way how we can represent our momentum right here, specifically in regards to the 0th component. So typically, side note here, typically p0 is equal to, or just defined to be, the energy of the particle divided by the speed of light, right? And the other components of the momentum are effectively, just other components of the momentum. It's what you have from classical physics, right? So using this definition right here, what exactly does our form momentum, or the magnitude of it, become? Well, we see here that if we just have, P0 times P0, that's our first term, right? And then we need to do the same for the other three terms. So we're just going to have minus, well, our normal momentum times our normal momentum. What exactly is this term right here? Well, this right here, we just defined to be E over C times E over C. So, E squared over C squared. And if you just want to solve for the total energy of the system, then we have E squared is equal to, multiplying both sides by C squared, M squared, C to the 4, and then plus, well, P squared C squared, where P squared is just the total value of our classical momentum. And that right there is one of the fundamental results of special relativity. You'll notice that if P equals 0, or if our velocity equals 0, then that second term is just going to go to 0, and we're left with E squared equals M squared C squared. And, taking the square root of both sides gives us E equals MC squared, the famous equation, right, of special relativity, which is actually pretty important because it shows that if our energy of, some particle, even if it has rest, it's not actually 0. It has some, intrinsic energy because it has mass. So now, here's a good question. We have a relationship between energy and momentum. How exactly can we get a quantum mechanics equation out of this right here? The method for converting this equation right here into one that is, quantum mechanical follows the method you would use for pretty much most equations when converting from classical mechanics to quantum mechanics. Just replace your energy and momentum values with energy and momentum operators, get those operators to act on some sort of wave function, and bada bing, bada boom, you effectively have an equation for quantum mechanics. So with that, what exactly are our energy and momentum operators? Well, they are just defined as such. So E, or rather E hat, because our energy now is going to be an operator, is just equal to I times the partial derivative with respect to time. And our momentum is similarly defined as P hat is equal to just minus I and then times the gradient right here, where the gradient is just going to be the usual operator from multivariable calculus. So let's go ahead and replace our E's and P's in this equation right here with operators and have them act on some sort of wave function. So we see then, moving all of our terms that are going to have operators in them to one side, we see that we have 0 is equal to M squared C to the 4, and then plus P squared is just going to be, well, the minus goes away, obviously, but the I is going to become negative. So this right here is actually going to become negative, and then the gradient just squared. And then our E term right here is going to become, well, minus, but it's already on the other side of the equation, so it's just a plus. Plus the partial derivative with respect to time, and then squared. And what's interesting about this is that this term right here is just equal to the 4 divergence. So, we could write this as just like partial, or sorry, 4 Laplacian really, sorry, as like partial squared and then mu. Another common way to write it is just with the D'Albertian square. And this right here follows a similar trend with many things with special relativity. It's the time component, the temporal component, having a positive value, and then all the position ones having a negative one. And again, I've said it before, but I'll write it out more explicitly. This stems from the fact that our metric right here is just going to be 1, negative 1, negative 1, negative 1. That right there is just our metric tensor, right? So because of that, it follows this pattern of the temporal component right here being positive and the rest of the values right here being negative, right? So let's go ahead and have this actually act on a wave function. We see now that we have this square right here, and then plus this m squared times c to the 4. But at this point, I have already kind of mixed notation. These operators right here are in natural units. Natural units. where we're assuming that c equals h bar equals 1, right? So just for simplicity's sake, so we aren't carrying around a bunch of terms with, c's and h bars. So really right here, I should have omitted the c squared. That right there is just implied in natural units. They're restored later with dimensional analysis, so the textbook says. So now we have the D'Albertian operator plus m squared, and then of course we need to actually act this out, put this operator onto some sort of wave function. So let's call that psi, as per usual in quantum mechanics, and then just say that right there equals 0, because that all has to equal 0, right? And this right here is actually just the Klein-Gordan equation. So Klein-Gordan equation. And this right here is one of the first equations of relativistic quantum mechanics. So now that we have this Klein-Gordan equation, how exactly can we get a Dirac equation from it? And the answer to that lies in the fact that this right here is a second order partial differential equation. And this actually makes it quite difficult for some of the solutions, because, if you think back to calculus, right, if you're solving just a first order differential equation where you just have like a y prime, well, you only need one initial condition. Whereas if you have a second order differential equation, you need two initial conditions. If you're solving like, for like the acceleration of something, or if you're starting with the acceleration and you're trying to get like position, like you do in Newtonian mechanics, you need, an initial velocity and an initial position. With this equation right here, you're going to need two initial conditions. And quite frankly, Dirac didn't really like that. For a variety of reasons. So, as the story goes, he was sitting by the fireplace and he wanted to make the second order equation into a first order equation. And what better way to do that than to factor it? So let's go ahead and try to factor, quote unquote, this Klein-Gordan equation right here, right? So we see here that we have a bunch of squared terms. So even though this operator right here, the D'Albertian, the little box is, just a box, it has a bunch of terms that are actually squared in it. So let's go ahead and basically just posit that this right here, this operator, can be converted into a form such that we have a partial t minus b partial x minus c partial y, and then minus d partial z, and then plus im, and then times, well, all of this right here. So all of this right here, I'll rewrite it real fast, and then just minus im. This is just, how you would normally factor something like this, just with a bunch of a, b, c, and d's. Now, if we were to FOIL this out, what exactly would we get? Well, obviously the cross term, so all of the derivative terms times im, and then times minus im, all of those are going to cancel out, so we don't really need to worry about those. What we do need to worry about, however, are the terms where a is multiplied by b, and then you're adding the other term, b times a, right? So basically we're left with this really wacky thing where if we were to FOIL everything out, yes, we have this handy D'Albertian operator, and then, plus m squared, but then we're going to have a bunch of just extra terms, right? We're going to have terms like a times b partial t partial x, or sorry, I guess minus ab partial t partial x, and then minus ba partial t partial x. And we don't want those in our equation. So in order to end up with our original operator right here, we need to apply a couple of conditions here. And those are namely, well, a squared has to equal b squared, has to equal c squared, has to equal d squared, which is just equal to 1, right? Because we don't want any extra numbers there. That right there is pretty straightforward. But then we also want all of these right here to just not commute with each other. So we have AB plus, BC, or sorry, AB plus BA. Been thinking about calculus too much. That right there has to equal 0. Or really they have to anti-commute with each other, right? Because, AB would equal negative BA. And this goes for, every combination of them, more or less. So what object have we created? We've taken, these derivative operators right here, and then we factored them, and we've ended up with something that shouldn't actually, with numbers that shouldn't actually commute with each other. We've gone from having scalar values in front of the derivatives right here, and instead we've turned them effectively into matrices right here. And the solution to this, puzzle right here, where, a squared equals b squared equals c squared equals d squared equals 1, and then all these anti-commuter relations, the solution to that is just the Dirac gamma matrices. So the solution to that, we're not going to derive them in this video. Might do it in a future Physics Friday, though. This right here is just going to be 1, 1, -1, -1. And the other gamma matrices are, interestingly enough, so gamma mu, are just going to be, well, zeros along the diagonal, and then just the Pauli spin matrices in the corners right there. So this is for mu equals 1, 2, 3. 1, 2, and 3. And from this, we can really get the Dirac equations, because now that we have, values effectively for, A, B, C, and D, we can just go ahead and substitute those in, and there we go. We have our equation. So let's go ahead and just take this one right here. So just this first equation right here. Let's go ahead and implement this. So we have, what all this becomes is we're going to have, the muth gamma matrix, and then times the 4 gradient right here. So this right here is just using the Einstein summation convention. It's just an equivalent way to write, a times partial t, and then minus b partial x, and so on and so forth. And then plus im. And that right there is just the entirety of our operator, right? So then we can just go ahead and apply it to some wave function. So, some psi. And that right there, as before, has to equal 0. We can actually just clean this up quite nicely by multiplying both sides by I. So we end up getting this m term just by itself. So we end up getting minus, and then an I right here. And that, ladies and gentlemen, is the result we wanted to get in this video. This right here is just the Dirac equation itself. There's a fun notation right here. I think this is some of the coolest notation, probably maybe in all of math and physics, is where, because we have so often these gamma matrices times, well, really anything, but a lot of the time it is a derivative, physicists have come up with a way to express this using shorthand, right? Instead of writing, gamma mu, partial mu, because, that's so much work. Instead, what we do is just, in this case, just I, and then partial with a slash through it, and that there's Feynman slash notation, and then just minus m. This is in natural units, by the way. Psi equals 0. And again, these are the same thing, just kind of a cooler way to express it on the right. But yeah, there we go. We have the Dirac equation. Next week, we'll investigate U1 symmetry in this field right here. And from that, we'll be able to derive Maxwell's equations that you find in electrodynamics. So I hope you enjoyed this video. Stay tuned for the next one. Thank you for watching.